Hello everyone, welcome to Advance Verilog Design with FPGA. We are from Logictronics and Digitronics So basically this course is on the Verilog programming, Verilog design and targeting FPGA design and VLSI design as well as verification. So we will talk in depth on Verilog programming language. So basically Verilog is the hardware description language. So we are going to have these lectures, and in this first section, so we are at first section of Verilog Basics. We will have few lectures. Actually all the lectures are included in the single video session. And first of all, we have the lecture first of Verilog introduction, lexical convention, syntax, etc. Lecture 2 is data types, string, vectors, integer, real. And lecture 3 is system tasks and compile directives. Lecture 4 is Dataflow Modeling, operators in Verilog. Lecture 5 is behavioral modeling, procedural statements as well as always an initial block. Lecture 6 is lab session, which is basic project with Verilog programming language, and we will utilize the simulators or simulation software, Vivado design tool as well as simulation software, and we'll also see the model sim from Mentor Graphics for design and simulation. So basically lab 11 is the lab session, and other lab 1 to 5 are the overview and theoretical sessions. So let's begin with lecture first. So basically you are already familiar with Verilog. Verilog is hardware description language, also termed as Verilog SDL. This is initially developed by Gateway Design Automation team. So they have developed this language in 83 to 84 of 1983 to 1984, and after that the language is standardized by IEEE, Institute of Electrical and Electronics Engineers, in 95. So it gives the standardization number of 1364, and Verilog have mainly 95 version revision, 2001 revision, and 2005 revision, and 2009 revision. Basically 2009 revision is termed as system Verilog. So basically we utilize 2001 revision in most of designs, but in this session we are going to talk about 95 as well as 2001 in parallel. So another thing about Verilog is maintained by non-profit organization currently. So there is Open Verilog International Group which requests and which maintains the language and follow the IEEE standardization procedure. So basically you already know about the high-level languages like C language or C++ language. Verilog can be termed as successor of C programming language. So Verilog is quite similar to the C language, and Verilog is heavily utilized and preferred for hardware design and verification in the FPGA design field, VLSI design and verification, or ASIC designing. So there is also another hardware description language called VHDL, which is also utilized along with Verilog. And another term we need to know about is system Verilog. System Verilog is like the extension of Verilog. Sometimes it is also termed or called as superset of Verilog. So most of features of Verilog are contained or included in system Verilog. However, some of the other features are also included in system Verilog which Verilog don't have. So it is heavily utilized. So let's go for the little bit about Verilog design flow. So in the first we have the Verilog code block. This shows that while we following the hardware design methodology, we need to know about the architecture, we need to know about the RTL code or VHDL or Verilog codes. So first segment of this flow is writing Verilog program or Verilog code. Then we follow the simulation. After writing the program, simulation is like a process of generating the virtual test setup. We can simulate the input parameters, so we can predict what will be the corresponding output on real time test. So simulation is like testing the design virtually. So after that we have the synthesized design. So after we simulate the design, we can go for synthesize. Synthesize actually checks the syntax, semantics, as well as it generate the RTL schematics. So we can analyze those things, and after the simulation completes, we can again go for simulation. Sorry, after synthesis, we can again go for simulation, and the simulation can be a repetitive process because simulation is just verifying the results, verifying the process. So we can do number of times simulation. And another part is implement design. So implement design is actually like mapping and planning the design or logical design or Verilog design with the hardware constraint. So hardware need to be mapped with logic or program. So this implementation phase did most of that job, and after the implementation completes, we can go for generate programming file and programming device. Actually the last option, this option is optional. If we are talking about the FPGA design flow, we will follow this generate program and programming device. But while in VLSI design, we only do the implementation up to implementation phase. So we can just map the things, map the logic and physical hardwares. So these things can be elaborated on this picture also. So this picture is started from setting up the requirements, writing the RTL code or BSDL or Verilog codes, and the simulation is run inside in parallel. And after that we have synthesis, gate level modeling, again simulation. Simulation actually utilize the test bench. Basically test bench is program or code for simulation, like if the normal Verilog program for simulation is test bench. Then after the synthesis simulation, we have relation route, timing modeling, timing analysis, again simulation, and we can go for ASIC or FPGA. So this is the Verilog design flow, which is follow on the overall design of projects or verification stops for VLSI as well as FPGA. So basically we have here the abstraction level on Verilog. So there are mainly 4 different abstraction level on Verilog. However, most of literatures talk about 3 different abstraction level. They talk about gate level, data flow level, and behavioral level. So there is also another level which is switch level. Switch level actually implements design on transistors, switches, or storage nodes. And if we talk about the abstraction level, actually abstraction is like the hiding information. So that is the main logic of abstraction. So basically switch level is the lowest level of abstraction. It gives lowest level of abstraction, and the behavioral level gives the highest level of abstraction. Abstraction just hides the information. So that means we don't need to, if the abstraction level is higher, we don't need to know much about the hardware level. Just the top level information is sufficient. If we talk about the lowest level abstraction, then we need to know more about the hardware level. That means like in lowest abstraction, we need to know about transistors, switch, storage nodes, even interconnections. So in the second we have gate level, structural level. So in this level we utilize, in this abstraction level method, we utilize like logic primitives like and or not, like logical gates. And third is data flow. So data flow level is also termed as RTL level. RTL level utilize some like assign statements in Verilog code, and this is like similar to the logical equations like K-map. So you might be familiar with K-map equations. Those equations are written up with assign statements. So fourth is behavioral or algorithmic level. So this fourth step is heavily utilized on Verilog codes because the Verilog programmer or the person who writes the Verilog program doesn't need to know about in depth about the hardware level. So behavioral level gives much more flexibility. So this is actually the Verilog programming methods which utilize the conditional statements as if else, case, and loops. So basically we can even sort out or even make the code in fewer statements or fewer lines than the switch level. So switch level needs lots of statements, but behavioral level needs very less. So it gives much more flexibility. So this is the abstraction level Verilog. So another is lexical convention. So lexical convention is like standard practice of syntax and semantics. So Verilog is like case sensitive. So uppercase is different than the lowercase. So if you are defining or writing the uppercase letters or variable name, then it must be case sensitive. So the same like rules or standard must be followed over the program. So there is like formatting of Verilog program. So we can write most of things in single line with statements, end of statements, and or we can just separated lines for like structure for better understanding. So another thing is comments. So comments is like the C language, C programming language, we can use double slash or slash asterisk and asterisk slash. So slash asterisk is for starting and asterisk slash is for like ending. So another is operators. So there are mainly three types of operators in Verilog is C language. So some operators are unary operators which only need a single operand. So here B is like operand, and this tilde is unary operator, so it just invert the B and gives the value to A. So another is like double AND, which is binary operators. The binary operator need two different operands, and ternary operator need three different operands. So they are the three types of operators, while there are subclass of operators also, like arithmetic, logical, relational, like other operators. And let's see one example of how to write like very basic logical gates. So while talking about the Verilog code, here we have 95 revision of Verilog code or Verilog module, which is termed as top module. So we have the time scale. This is like primitives, like directives, compiler directives. So this compiler directives actually instruct the compiler for like some background setup. So we are just writing dash time scale 1 ns by 1 ps. So this signifies that we want our timing variables need to be nanosecond by picosecond precision. So it gives the precision of timing which can be needed on the program. So the picosecond gives us up to picosecond of precision. So if we write like timing variables with some value, then it will count up to picosecond, which we also going to talk on next slide. So we have the very basic module, and the module name is AND gate, and the parameters for AND gate is A, B, and Z. So all the orientation of A, B, and Z are listed here. So input A, input B, output Z, etc. And we have the assign. So assign is the statements for assignment. So these have assign space, output port is Z equals to A and B. So what happens is ending of A and B will be presented or will be assigned to Z. So this is the very basic assign process or assign statement. So this is the Dataflow Modeling code, and we have the in module. So this is very basic top module. So let's see about the simulation test bench. Actually, simulation test bench is code for running the simulation. Like the top module, we have here some timing precision, and simulation test bench consists of some one empty top module. So module and get underscore TV. Actually, the simulation test bench module name is different than the top module, and it consists of some registers. Like registers is for storing some information for short time, and the wire is for connecting some sort of values to another port or another variables. So registers and wires are instantiated here. Then we have the top module. So this section is actually the top module section. So top module section actually map or connect the simulation test bench with top module. So we can see AND gate UUT. So UUT stands for unit under test. So this is the mapping section. AND gate is the top module AND gate, and top module is called here, and port of top module A is connected to register A, B is connected to register B, Z is connected to wire Z. So these three things are those with separated with comma and started with full stop. And the AND gate DUT has been closed here with semicolon, and we have initial begin. So initial begin is the starting of stimulus. Stimulus stands for set of input values or parameters, so we can generate the output. So for basic AND gate, we have four different set of values. We can have 0 0 0 1 1 0 and 1 1. Each set of values are separated by hash 100. So this hash 100 is actually the timing unit. So what the timing value is, we need to have nanosecond by picosecond. So this stands for 100 nanosecond with picosecond precision. So if we write 100.0001, then it will work for corresponding 100 nanosecond with some remaining picosecond value. So we have separated by 100 nanosecond for each set of values for this AND gate, and we have the end. So what happens is, so while the simulation runs, it will generate the corresponding output of Z. So we have the Z, so output is Z. So Z will be generated with this input correspondingly. So if there is A is 0, B is 0, then Z will be 0. A is 0, B is 1, again 0 will be 0, 1 0, again 0 will be 0, 1 1, there will have 1 value. So because we are doing AND gate. So this is very basic logic gate. So let's go for next one. So we have here another important thing. So as we talked in the previous, Verilog have mainly 95, 2001, 2005 revisions. So among those three major revisions, 95 revisions is also utilized heavily, and another most preferred revision is 2001. Actually 2001 sort out few lines of Verilog 95 in single one. So we can see the Verilog 95 consists of module name and ports and orientation of ports, and 2001 revision have module name and ports with orientation in same line. So we don't need to have other extra lines, so it just reduces the length of code or length of module instantiation. And after that we have assign. Assign is same in both 95 and 2001, and in module is also same. So just the first ports orientation initialization or the definition section is different in 95 and 2001. So these basics. So another thing we need to know about Verilog is size and unsize number specification. Verilog numbers or variables can be assigned with size numbers or the unsize number. Size number means this signifies 4-bit binary 0001 value. This signifies 16-bit hex D2 AA value. So numbers can be negative, or for better readability, we can just separate the numbers with this type of underscores. And actually Verilog consists of data types of X and Z also. X is for unknown value, and Z is for high impedance value. So if we want to extend any numbers, we can have this type of statement. So this signifies for multi-bit definition of A is registered with 12-bit, and A can be put the value of X. So A will get 3X while we providing the hex value. So this is for how to sort out the lengthy variable number with small representation or small specific value. So another thing is string. String is like the C language. We use inverted comma for presenting the string, and identifiers is here. Identifiers means how we can define the variables, how we can generate or how we can create any new projects with names or anything constants. So basically we can't use the resolve keywords, system tags, compile directives. We can have the variable name with alphabetic characters like and underscore gate, or we can just start with underscore and gate, etc. And we can have this type of process followed. So here we have an example: register space underscore digitronixnepali. So this is one register type of variable. So like you see, it is case sensitive. So if we define digitronixnepali in this manner, we have to utilize the same manner in the remaining program. So as we talk data types, so there are 4 different types of data types in. So guys, let's begin with lecture 2, data types. So we already talked about the basics of Verilog and other things up to the different type of number format and size and unsize number format. So data types, we already talked a little bit about this type of data types. So Verilog have 4 different value labels. So that is 0, logic high or logic 0 or false, 1 for logic high or true, X is for unknown, and Z is for high impedance. So basically 4 logic labels. And nets, actually nets stands for wires. Basically we use the wire keyword. So wire is for defining any sort of like connecting points or connecting jumpers. Like in physical connection we use jumpers. Wire is jumper for Verilog program. So wire can be have like a single bit or multi-bit type of wires, and it can be represented by wire. The size of wire is defined here. So there is MSB down to LSB and the variable name. So data underscore A is wire type of 8-bit. So this is the basics of nets. And another is registers. So registers is like storing some values with variable. So like is the hardware based registers, it stores the value for sort of time. So we can have a specific value until the next value like replaces the register value. So register reg is the keyword, the variable name is dxy. So we can have the like initial begin, and we can put some 1-bit binary value to dxy. Actually dxy is 1 bit, and change the value by first giving the 1 and second giving 0 with 50 time unit delay. So the delay is specified with #50. So that means the overall unit of delay is 50. So it depends upon the time scale compiler directive. So it represents timing like parameter. So let's go for next, which is vector. So vector is like defining multi-bit variables. So like wire A1, it is a single bit, so it can also be called a scalar. Another is wire 15 down to 0, which means 16-bit wide variable name is ADBus. Another is 30-bit wide different variables, group variables like pos x, pos y, pos z. All 3 are 32 bits wire. And we can have even registers with scalar and registers with vectors. If we want to select a specific like vector variable, then like we can assume like pos x is 32-bit wide. So if we want to access the 7th member of vector, then we can like access this type of way. So we can also select a specific group. So ADBus is selected. Actually ADBus is 16-bit wide, we just need 4-bit. ABC is here, so ABC is like 40-bit wide, and we just need like 8-bit. So the ABC definition is a little bit different than the other one. So it have MSB value 0 and LSB value 39. If we define like this, then we have to access like this type of way. So MSB must be 0 again, and LSB can be varied. While the previous definition way consists of MSB is higher bit and LSB 0. In their condition, MSB is higher bit, LSB 0. So this is very basics. And if we want to like declare multi-bit inputs, so here we have an example for exactly the same module AND gate, module space AND gate, parameters ABZ and input, the width or size of our vector definitions, and A is variable name. So A is 2-bit input, B is 2-bit input, Z is 2-bit output. So assign Z equals to A and B. A and B will operate it, and that means the result will assigned to Z and in a module. So if we want to define like single bit variable in this format, then we can define like this. Single bit means normally input space A works for single bit. If we want to define like this type of MSB into LSB way, then we can have this statement. So let's go for next one. So integer, real and time registers. So in this integer, real and time, so integers like in the C language, we can have integer space counter. So counter is integer type, and we can have integer value. Integer value means it consists of negative or positive numbers without decimal places. So real value actually consists of decimal places. Decimal places like 3.14, while integer only consists of plus minus numbers without decimal places. Real value also can like can allow to use scientific notations like 3e6. So this is for 3 into 10 power 6, it must be. So this type of notations can also be utilized. Here are some examples. Real D1 D2 initial begin. D1 is provided by FOI 10, D2 is 3.25 in. So initial begin in is here. So we have here integer J, so J is provided to D2. D2 is actually 3.25. So if we like define any variable with real and we want to pass that real value to integer, then integer will neglect the decimal places. So this is the example. Another is time. We will talk about time. So time is like defining the simulation time. So we can have like time type of variable. Time is the keywords, time space variable name simulation time, SIM time. Initial simulation time is $time. So $time actually takes the specific time, that means current time. So it gives the current time. So if we want to show the current time on the like console, then we can use $display bracket %d comma $time. So $time is the current time. It will display the like current time. The %d the identifier which will display the current time. So another is array. So array is like the vectors, but it is a bit different than vectors. Vectors is actually written up in the front of or the left hand side of variable name, while array is defined right hand side of the variable name. So array is like vector is same variable with multiple inputs. Array is combining such multiple input or the single input variable in number of such variables. Like number of vector type variables is array, or number of variables is array. So vector is like single variable with multiple inputs. So like single computer with multiple display and multiple computers. So multiple computers is array, single computer with multiple displays like vectors. So this is the main logic behind the array. So let's go for one example here. So example is like how to access the elements of array and how to like store the corresponding value in array. So we are in lecture 3, which is system tasks. System tasks is like how to utilize some system based keywords functions. So it can be like showing up the information. For displaying information, there are some display. So display can print out the current time as we talked previously, and there are mainly system tasks of display, $write, strobe, monitor, and these things are this system tasks can be utilized for different type of information swap or displaying. So we can display binary, decimal format of information. So we have here format specifier. So the for like printing or for displaying the binary numbers, we need to have %d. %b can be of small or capital. So if we want to display the string, we need to have %s. Time format is %d. So we have here display keyword. So display keyword show up the information which is followed with the inverted comma, and write is also there. Write and display are quite similar, but write display actually prints out the new line character also. Write does not. Write only like prints the current thing. So display is much more good for like showing up multiple lines of information. Strobe is utilized for simulation events. So strobe prints the any change. So strobe actually prints the like specific events when the current time is executed. So it also utilized automatically, or automatically it's a new line. And monitor is like utilized for monitoring the any specific line. So if anything changes, it will show up the information. So like if anything trigger it will show up the information. So strobe just print out the specific events on specific times. So we have here monitor actually have monitor on and monitor off keywords also, and it checks specific parameters. So if that parameter is changed, then it will fire or the show up the information. So we have here example of monitor. So it checks the clock and reset. If those things are changed, then it will show up the information like within some interval of time. So we have initial, begin, and end. So these things are the default one, and $monitor is the information displaying system tags. So clock will be displayed and other thing will be displayed. So stopping and finishing simulation are also some like keywords on Verilog, and starting or stopping, these keywords can be utilized on. Another is compile directives. So we already talk about the define, we talk about the time scale. Along with those, there is include, there is resettle, and there is unconnected drive, no unconnected drive, if define, else if, such type of compile directive. So reset all is like a directive for resetting everything. No unconnected drive and unconnected drive are utilized for like connecting and unconnecting the input ports of the modules. So it can be pull down or pull up at the by the like directives. And this line number just show up the specific line number. Another is define and another is include. So include can be utilized for including any files like any sub programs or functions written on another file. And main thing we utilize is time scale. So it just gives the time precision. So 1 nanosecond 1 picosecond gives us 10 to the power 3 up to 10 to the power 3, that means 3 digit after decimal precision. So we are at now Dataflow Modeling. So Dataflow Modeling is like we already know about utilizing the Verilog design method with assign keywords, and it is very basic, and we implement some sort of like logical equations in Dataflow Modeling. And here we have an Verilog 95 examples for mux, 2:1 mux. And let's see again here. So the mux have module name of mux21 Dataflow. Some inputs are listed here, orientation of inputs are here, and we have the assign output port will get the right hand side result, operation results. So this is from the like K-map of multiplexer, 2:1 multiplexer. So it can be signified here when S0 is 1, output will get 0 and I0, 1 and I1. So that means we are doing ANDing operation. So yes, 0 is 1, the I1 will be provided to out. Yes, 0 is 0, I0 will provide to output port. So this is the very basic of 2:1 mux. And we have some operators here. So bitwise operators. So bitwise operator performs bit by bit operation. Like here we have A, B. So it computes the bit by bit operation. And if the like length of any operand is not equal to the output, then it will be 0 extended. So another operators is arithmetic operators, plus, minus, asterisk, division, remainder, and multiplication. And we have small operations of multiply, accumulator. So it did the arithmetic operations. And we have the divide operators. So it did the arithmetic operations. So result of expression, that means if any like variable have less size of width or less size than the output port, then some 0 will be extended. So if the output is more width or more bit size than the output port, then some output will be like terminated. So this type of method is follows. Like here we have C. C is 4-bit, A and B are also 4-bit, so result will be provided to 4-bit C, while we have here D is like 8-bit, and A is 4-bit, B is 4-bit, and E is 7-bit. So what happens is 0 is added on this type of operation, so the D output port will get overall 8-bit result. So we have here concatenation and replication operators. So concatenation means like appending or appending the multiple inputs or multiple bits, so it will be much more flexible for designing, like while like checking or while checking the conditions of multiple variables by single variable. So we can use concatenation, so it just can be expressed with curly bracket, and we can see here the overall curly bracket is starting from here to here. Actually, Y will get first A in the MSB, C1 in the LSB, and the mid value is B0. So all the value will be arranged and concatenated. MSB to LSB is the curly bracket covers. So another is replication operator. So replication operator actually replicate the same information. So we can replicate the information. So like the this type of statements 2 dash B01, that means 2-bit binary 01 value is replicated by 3 times. So this replication operator is also utilized for doing the same operation multiple times, and we can see some output. So replication of 0x7, that means replicating 0x7 3 times is 0x777, that means they replicating the value 3 times. So here we have an example of basic operations, which is 4-bit adder, and another is reduction operator. Reduction operator actually like multiply or the operate the bitwise operations. So the reduction operator is unary operator, so it did the operation by own bits. So like this statements and of 4-bit binary 1001 is 0, because it just and 1 and 0 and 0 and 1, so overall result will be 0. So reduction operator did the bitwise operation of single vector operand, so finally gives the 1-bit result. So now this is logical operator. Logical operator can be like a logical AND or logical or negation. So logical AND is like for actually this type of operator gives the true or false result, so 1-bit result will be given. So if any like undefined or high impedance value is in the condition, then it will give the undefined result. So like we can see A will get the value of C logical OR of D. So that means C logical OR of D, if the logical OR of C or D is 1, then it will get the or C logical OR D is true, then it will get the 1 value, and the ANDing operation, that means logical AND means it generates the logical results. So mainly this type of variable or this type of operator utilized for like comparing if else condition. Another is relational operators. Relational operator means like basic relation with greater than, less than, greater than or equals to, and less than equals to. So we can have multiple type of relational operator examples. And another is equality operator. Equality operator have logical equality, inequality, case equality, and case inequality. It will also give the true or false result. So we have here some examples, like we have some A, we have some B, and X, Z, etc. So if double equals to B, that means logical equals to B, that means A have value of 4 and B have value of 3. So they are not logical equals. Logical equals means the value is not logically true, so it will generate the 0 value. And while we talking about the like case equality and case non-equality operators, so actually this case equality and case non-equality, that means double, triple, equals to and not double equals to checks individual bits, so it needs to be checks with individual operand bits. So if the all bits are true, then it will give the true result, or it will give the false result. So we can see Z have, let's see for x have 4-bit binary 1010 and y have 4-bit binary 1101. So we want to have like x is double equals to z, that is logical equals to z, so that is not true, so it will give the like undefined result. So if we check the z and m have same value, it will give the logical 1 value. So this is the example. Another is shifting operator. Shifting can be left shift or right shift. So arithmetic shift, we can see an example here. 4-bit binary 1001 is shifted left, so it will like left by 1 bit, so it will gives 0010. 0 will be added on the right hand side, the LSB value. So if we shift just reverse, then what happens is we can see here. So 4-bit binary 1001, and it will shift like in the 0 will be added on left hand or MSB of the input. So there is also conditional operator. It checks the condition. If the condition is true, then it will gives input 1 to output port, else it will give output 2 to the output port. We have here a multiplexer design, so we are defining with multiplexer. So we are at lecture 5 of behavioral modeling. So behavioral modeling actually consists of procedural construct. So in behavioral modeling, we utilize initial and always block along with like conditional statements, if else, case and loops. So initial block is like start from initial, and it can have single line statements, so it can be represented with initial only for single line statements. So if we have multi-line statements, we can have initial, begin and end. So this is very basic style. And so for instantiating any values or the constants, the variables, we can do this type of statements like reg clock initial, clock equals to 0, that means initializing the 0 value to the clock variable. So we have here Verilog 95 and 2001 revision example. So we already gone through this example. So in 95, all the ports are listed first and orientation are write down later. But in 2001 revision, orientation and ports are already listed in same line. So the code will be like have less number of lines. So another main important thing is always block. Actually, always block runs on parallel, so it is utilized for executing any sequential statements like if else, case statements. So always block is always needed for like conditional statements or conditional statement based programs. So it also consists of the sensitivity list. Actually, sometimes we need to have like we have here always @ in bracket we have x or y or c in. So actually x or y or c in are the sensitivity list. So if the like x or y or c in changes, the overall operation result will be changes. So when these things change, always block perform the operations again. So this signifies for sensitivity list. So we have all the sessions up to here. So we'll go for lab section, which is lab 1-1, and we'll do this writing very basic logic gate in Vivado tool and simulating the design on Vivado, as well as we also simulate the design on Model Sim. So guys, thanks for watching. Meet you in next section 2 video. Thank you for watching.